Hello, this is the second in a set of videos on testing between two populations. And in the previous video, we discussed testing for a mean difference between two populations assuming independent samples. That is, I have one independent sample from one population and another independent sample from a second population. But there are also many scenarios where two-sample testing is done using dependent samples. And the most common case is what is called paired testing, sometimes called before and after testing. And in this scenario, we collect the samples from each population in pairs. That is, we've intentionally collected these so that the measurements have some correlation between them. And the rationale for paired testing is that I'm only interested in determining if there is an overall mean difference between each of the two populations, and I'm trying to filter out the sample-to-sample variation. In the standard two-sample t-test with independent samples, I'm forced to incorporate all the variation between the samples, or sampling variation, into the test, and this adds additional noise, which makes it difficult to see if there's really a difference. In paired testing, I collect all observations in pairs. For instance, collecting measurement of blood pressure before applying a treatment, and then measuring blood pressure after the treatment, and each pair of measurements are made on each subject. It's a very, very common type of testing used in many different disciplines. So in paired testing, instead of testing for a mean difference based on the raw data, my test is based upon the difference between the paired observations. In other words, the two-sample test is turned into a one-sample case. And because I only look at the paired differences, any potential differences that may exist or variation between the samples is simply filtered out. Okay? And we're going to illustrate this using some examples. And instead of using the example in the notes that builds on the aluminum lithium data, I'm actually going to use another example, and this is a data set from a cholesterol study. So we have 11 subjects, and their cholesterol is measured prior to going on a low cholesterol diet, and then the cholesterol is measured post diet, in other words, after they've been on the diet for some amount of time. In other words, this is a diet, basically it's diet and exercise, and they want to see if it can effectively lower cholesterol. But you also notice quite naturally, for instance, look at 10, 480, I think it's milligrams per deciliter. But you can see it's quite high. On the other hand, some of the other people, like number 1, is quite low, and this is natural subject to subject variation. But I'm not really interested in that. What I'm interested in is studying an overall mean difference. So I'm just going to create an additional column where I'm going to show you the subtracted differences post and pre. Okay. We don't actually have to do this. I'll show you in a moment. JMP will actually do this for us. But just for illustration, I'm going to call this the difference. Okay. So I'm going to right click on the highlighted difference column and select formula from the drop down menu. And in the formula editor, I'm just going to create a formula which is post, go to the keypad, minus pre. Okay. So notice I'm now only looking at the differences, and this is a way of filtering out all the person-to-person variation, reducing the amount of noise in the measurements. In other words, it's a way of filtering out noise so that I can do a test for an overall difference. So paired testing is very common, as I said, because it is a nice way of filtering out variations so you can actually more clearly see if there's a difference. So I'm going to go to the Analyze menu, and in JMP, paired testing is so common they have an option in the Analyze menu called Matched Pairs. So I'm going to just take my two paired columns and put them in Y. Okay. So JMP will actually compute the differences. Okay. And then we get the report. And the key to the report is to take a look at what is actually a one sample t-test for the paired differences. And notice this is borderline if you use the 0.05 criteria. Given there are only 11 subjects in the sample, I would reject the null hypothesis, and I would assume that there really is some effect of the diet and exercise program, and you are given a 95% confidence interval. And notice that again, 0 barely fits within this confidence interval. So there is some evidence. Again, you'd really want to go out and get more data given how small this sample is, but there's some evidence that the diet and exercise program may have worked. And as before, I'll just quickly show you, our null hypotheses have not changed. It's just the manner in which we conducted the test. So we test under the null that mu1 equals mu2. I'm just doing the two-sided test. And the alternative they're not equal. So in this case, I'm going to reject the null and accept the alternative. So we believe the diet and exercise program has some efficacy to lower cholesterol. And by the way, if you're interested, the way the test is done, the numerator is the difference average divided by the standard deviation of the differences divided by the square root of n, which would be 11 in our case. And then this is compared to a student t distribution with 10 degrees of freedom. So in this case, we're going to go ahead and reject and assume there is a difference. Now, if we hadn't done this in the two sample paired mode, and we had done it with assuming independent samples, then we actually would not have seen a difference. And I'm going to quickly illustrate this. By the way, if you compute the difference column, you could actually do the one sample test in the distribution platform, but we don't really need to do that. What I'm going to do is show you what would happen if I did these tests independently. Okay. So I'm going to go to the Tables menu, and I'm going to stack the two columns, pre and post. Okay. So in my new data table, I'm going to go to Analyze, Fit Y by X. So this is no longer being treated as paired. Label is X, and data is the response. And I go ahead and I'm going to do the two sample t-test. And then notice we get this large p-value indicating there is no effect. The computed difference, mean difference, is the same. The key is the standard error of the difference is now much higher because I've incorporated all the sample to sample variation. So paired testing is typically done by design and is preferable whenever possible. And when you're dealing with paired data, it is imperative not to do the inappropriate test, which would be the standard two sample t-test, but rather do the paired t-test.